The mean hourly pay rate for financial managers in the East North Central region is $32.62, and the standard deviation is $2.32. Assume that these pay rates are normally distributed. A. What is the probability that a financial manager earns between $30 and $35 per hour? And B. What is the probability that a sample average taken from a sample of size 30 financial managers is within 75 cents of the $32.62 population average? Okay, to start this, I've noted that the distribution is normal, and I've set up a probability distribution for the first part there. The standard deviation is given as $2.32. And the question is, what is the probability that a randomly chosen financial manager would have an hourly pay rate somewhere between $30 and $35? To calculate that, we know, or we are told, that the distribution is normal, and our normal density function, we will find the area under that above the interval. And to do that, I will need to calculate z-scores. So let me get the z-score of the 35. 35 subtract 32.62 divided by the $2.32 standard deviation gives me 1.03 as my z-score. And calculating the z-value for the $30 pay rate, again subtract the average divided by the standard deviation, and I get a negative 1.13. So I'm going to take these values, these standard deviations, and I'm going to look those up in the standard normal table and find the values, the probability values from that. And the table gives me, for a z-score of 1.03, the area to the left of that as 0.8485, and then looking up the negative 1.13, I get the area to the left of that is 0.1292. So to find the area that I want above the interval, I need to subtract those two values. So let me complete this statement. The probability that the z-value is between negative 1.13 and 1.03 is 0.8485 subtract 0.1292 to give me an answer of 0.7193. Or 71.9% approximately. So if I go into this population of financial managers and I select one financial manager at random, what's the probability that his hourly pay rate will be somewhere between $30 and $35? The probability is 71.9%. Another statement I could make is that of all these financial managers, 71.9% of them make somewhere between $30 and $35 as their hourly pay rate. This first part of the problem is using a population distribution and asking a question about an individual in the population, the probability that that individual is somewhere in an interval. The next part of the problem, we're going to change it a little bit. Now we're going to take a sample of 30 financial managers, calculate the average on that sample, an X bar, and then ask a question, a very similar type of question. What's the probability that that sample average will be within a certain interval? Now the problem asks us to calculate the probability that the sample average, taken from a sample of size 30, that the sample average will be within 75 cents of the $32.62 population average. Or we're talking about an interval from $31.87 up to $33.37. The distribution that we're going to use here is not a distribution of the individual financial managers. It's a distribution of sample averages taken from samples of size 30. The central limit theorem guarantees that the sampling distribution is normal for samples of size 30 or greater. So in looking at samples of size 30, I'm going to approximate that with a normal sampling distribution. So to calculate the probability that a sample average taken from a sample of size 30 is within 75 cents of the $32.62 population average, I need to calculate the area under the density function above the interval. The density function is normal by the central limit theorem and has a standard deviation, also called standard error, of $2.32 divided by the square root of the sample size, in this case 30. And that calculates out to 0.424, or about 42 cents. So the standard deviation of the sampling distribution, the distribution of the sample averages taken from samples of size 30, the standard deviation is 42 cents. To calculate the probability that a sample average taken from a sample of size 30 will fall somewhere between $31.87 and $33.37 is going to be calculated by finding the area under the density function above the interval. The density function is normal because the sampling distribution is normal. I'm taking samples of size 30 or greater. First thing I need to do is calculate a z-score. So I'm going to take the $33.37 on the upper end there, subtract the population average, $32.62, of course that's 75 cents, divided by the standard deviation. The standard deviation of the sampling distribution, since we're talking about sample averages here, is the standard error. It's calculated through a formula, is 42 cents, about 42.4 cents. When I calculate this, I get 1.77 as my z-score. So the z-score for 33.37 is 1.77. Now, since I'm exactly the same distance on the other side than by symmetry, I don't need to calculate this. It's just a negative 1.77. Now, looking these values up in the table, the area to the left of the 1.77, which I'm shading here in blue, is 0.9616, and the area to the left of the negative 1.77, which I'm shading in green. Looking that up in the table is 0.0384. So completing my problem here, the probability that the z-values for the endpoints of the interval fall between negative 1.77 and 1.77 is equal to 0.9616 subtract 0.0384 to get my probability of 0.9232, which I can write as 92.3%. Now, looking at the two problems that I've done here, I want to make a comparison again between working with a population of individual values and then a sampling distribution of sample averages taken from samples of individual values. They're very similar in one way, that they're both modeled by the normal probability density function, and therefore the mechanics to actually calculate the probabilities is very similar, since we're using the same density function and the same table of values. But there's a big difference between the two. One is asking the probability that an individual value taken from a population is within a certain interval, and the other is asking the probability that a sample average taken from a sample of individual values from a population is within a certain interval. Make the distinction between these two types of problems and think about how you would identify them on an exam. One is sampling and the other one is not. One has a standard deviation that is the population standard deviation. The other has a standard deviation that's calculated by taking the population standard deviation and dividing it by the square root of the sample size. The 42 cents in this second part of the problem is the standard deviation of the sampling distribution. I hope this has helped. Please read the problem again and look at this example to see the differences between the two, and think about how you might recognize the two different types of problems when you're on an exam.